Okay, so look at this example then. So, shop sign, so we're back to a laminar by the looks of it. I don't know if it says that. There we go, uniform laminar. Weight, 40 newtons, not labelled on this time, so we'll label it ourselves. Equilibrium, biggest point to pick out in this one, because we've not looked at one in equilibrium yet specifically, I don't think. Vertical, horizontal diagram, models, uniform laminar important, and then these, which I think some of these are not labelled on, some of them are. Right, so I'm going to draw my own slightly bigger diagram because I can put on what I want that way. So, T1 force acting there. I'll use a different colour. Just go back to, in fact, yeah. So that's T1. That's T2. That's T3. They're the forces. It's also got a weight, so because it's a uniform laminar, it's going to be in the centre. And it's going to go that way. And we're told the weight is 40 newtons. Then I want my distances, but I'm going to half them. So A to B is 0.5 meters, but I don't know quite yet where I'm going to need to put. Haven't quite figured out yet which ones I need to have half of and which ones won't need. So I'll just put them all on in half. So A to B, so there to there. Put on as 0.25 meters. Same again. 0.25 meters. And then A to D is 0.4. So I'll put it on as 0.2 and 0.2. Chances are probably one of them is the whole distance and one of them is the half. It tends to be how these ones work. I'll put my vertices on. A, B, C, D. Right, so this question is in equilibrium. I could spell equilibrium, that would be helpful. Now, there's three things we can do when the questions are in equilibrium. One is that we can say that forces going up are equal to forces going down, not moments, just the forces. That will be important in the vast majority of cases. One that's only really important when we're doing a laminar is that forces going left equal forces equals right. Because if we're doing a one-dimensional rod or beam, we won't really have any left or right forces in AQA. And then we can do the moments, of which the sum of the moments going clockwise and anti-clockwise should be 0. Okay, so that will effectively be in equilibrium as well. Right, so the first thing I'm going to say is the forces up equal forces down. So I'll say forces up equal forces down. So T1 is going to equal to 40 newtons. So we've already got one of our answers, which is nice. Start. I'll then say the forces left equal to the forces going right. So T2 equals T3. So looks like that will be useful, but it's not that helpful at the moment. And then I'm going to take moments around a certain point. So I'm going to take moments. Usually you will see an arrow, a curved arrow like this, saying you're taking moments with a point that you're going to take moments about. Now I'm going to take moments about the point A, and the reason is this. If you take moments around any point, you don't have to. You can ignore the forces acting at that, the turning forces acting at that point, because there is no perpendicular distance from that force to where it is. There isn't any distance, it's at that point. And imagine pivoting something and then pulling it at the same point, it's not going to turn. So I want to try and get rid of as many forces as I can. So taking moments at the place where there's most forces or unknown forces is generally a really good idea. I've then only got two remaining forces. So first of all, I'll look at the clockwise moment forces. So if I'm pivoting there, this one looks like it's going to be the clockwise moment. So that's going to be 40 newtons times by this distance here. That's the distance from that to A, and that's 0.25 meters. So I did need the 0.25 in that case, and that looks like it's going to be 10 newton meters. Then I'll do the anti-clockwise moment in this case, which is T3. So I pivoted there, pull it up and around, and then I think, as I alluded to before, I probably need the full distance in this case, which is 0.4 meters. So that is 0.4 T3 Newton meters. Now, because we're in equilibrium, it means that the clockwise moments equal to the clockwise moments equal to the anti-clockwise moments. So I can now say that 10 equals to 0.4 lots of T3. I can divide both sides by 0.4. I feel like I should be able to do this in my head. 25, so that's 25 Newton meters. So just a little round up. T1 we found at the start is 40 Newton meters. T2 we're told is the same as T3 because we're in equilibrium. The horizontal pulling forces are the same, and we've just found T3, which is also the 25 Newton meters. So that's R3. So a couple of tips. Use these three things. I think if you do any of the Mad as Maths questions, they always list these three things. The top two are always kind of ignored a little bit by some people. The second one will only be relevant on a laminar generally. And take moments around a point that is going to get rid of some of your unknowns. Okay, make it really clear what you're doing in terms of your moments as well.